5 minutes.
Yeah, I took some time to clean blackboards. Okay, welcome everyone back. The second talk of this afternoon session is by Leonardo Garcia-Heveling from Radboud University, and he will tell us about time functions with and without manifold structure.
Yeah. Thank you for the introduction, and thanks all for being here on a Friday at 2:30, and thanks to the organizers for having my talk. So actually, compared with the program, I changed the title a bit because it just said without manifold structure, but I decided to present also one result that needs manifold structure, so I have both. So first, well, this is the outline, so I'm going to give a quick introduction about time functions. Then I'm going to give the result about time functions on Lorentzian length spaces, which is the part without manifold structure. I'm going to give a sort of application of that, which is topology change. I'm going to say what that means. And then I'm going to talk a bit about completeness of the null distance, and here it's where I'm going to do it for manifold. And then I will mention some open questions about all of these topics. So first, time in general relativity. So compared to Newtonian gravity, for example, in GR, there is not an independent parameter of time, but time is part of space-time. But we can still have a notion of time in the following sense, which is we have a continuous function from our space-time manifold to the real numbers, and we call it a time function if it's strictly increasing along all future-directed causal curves. So think that the future-directed causal curve could be the trajectory of an observer, and for all the observers, as you can see, the time is increasing, right? So these exist if and only if the space-time is stably causal. That was shown by Hawking, although the paper is not very mathematically rigorous. So later it was shown indirectly by Minguzzi, and then more in the style of Hawking, but with more details by Crucial, Grant, and Minguzzi. And one thing that I want to mention is that in some cases there might be a canonical choice of time function, for example, in the cosmological setting, but even then it's not the unique choice, and there's never a unique choice. So but it makes sense because still in relativity we said that time is not an independent parameter, so it would be weird to have a unique choice. Okay. So now I'm
sorry, what is stably causal?
Oh yeah, sorry, I should say that. So causal means that there are no closed causal curves, which has interpretation that there's no time travel. And stably causal means that you're causal and this property is robust under small perturbations of the metric, which is kind of physically important because otherwise you have kind of a fine-tuning problem that, you know, if you perturb a bit, you lose the causality. Okay, so now I'm going to say first what are Lorentzian length spaces. So as you've seen in the previous workshop and maybe also in this workshop, it's often good to see Riemannian manifolds as a part of metric spaces. And then one can ask, can we do the same for Lorentzian manifolds? And there is a concrete proposal by Kunzinger and Seemann of how to do that. And I'm going to explain the basics of it. So basically, we have these 5 structures where XD forms a metric space. This relation plays the role of the causal order. And then we also have a chronological order and the time separation function, but they will not play a role in this talk. And then we need some compatibility assumptions between all of these structures. And I just want to explain one that is the one that will play a role for us now, which is called causal path connectedness. And it requires that for every pair of points that are not the same point and that are causally related, there should exist a causal curve in the sense of a Lipschitz curve that such that consecutive points on the curve are causally related. And with this, we can do causality theory, and in fact, these 2 papers, the original one by Kunzinger and Seemann, and then this one by Akehau, Cabrera, Pacheco, and Solis, they replicate the whole causal ladder of spacetimes in the setting of Lorentzian length space. And so the result that I want to present is the following one. So we have a Lorentzian length space, and we need to assume that the metric space is Sanko uncountable and proper. or separable and proper equivalent. And then we can show the following. So it's equivalent to be globally hyperbolic, to have a Cauchy time function, or to have a Cauchy set. So what does each of these mean? So globally hyperbolic means non-total imprisoning, which means that for every compact set, if I have a future-directed causal set causal curve inside, then after a finite d length, it has to leave and never come back. So it's not allowed to like accumulate in a compact set. And then the compact causal diamonds, which I think you've heard about in other talks. So just the points that are causally kind of sandwiched between two given points. This should form a compact set. And then a Cauchy time function. So this is a time function. So it increases along every future-directed causal curve. And moreover, we are requiring that if the curve is inextendable in both directions, then the time function should go to plus infinity in the future, and it should go to minus infinity in the past. And then a Cauchy set is a set that is intersected exactly once by any such inextendable causal curve. And one implication that is kind of trivial is from 2 to 3, because if you have a Cauchy time function, then the level sets are Cauchy sets, okay? Which in the smooth setting are called Cauchy surfaces, but here it's not clear what surface would mean. Okay, and this theorem was known since the 70s for spacetimes due to Giraud. Then later Bernal Sanchez showed that this time function can be shown to be smooth, not just continuous. And it was also generalized to C0 metrics by Zeeman. So this is a central theorem in the manifold setting, and we have generalized it to Lorentzian length space. And now I'm going to give a bit of a proof sketch. So first, just in the manifold case, how is the classical proof of this theorem? So, and I'm just going to focus on how to construct the time function. So first you choose a Borel measure that should be a finite measure. It should give non-zero mass to every open set, and it should give zero mass to the boundary of the past of every point. Okay, and then, for example, you could take the Lebesgue measure and then multiply it by some function to make it finite. And then you set the time function to be the measure of the past of the point. Okay, and I can explain quickly why this is a time function given our assumptions. So first, because of the first assumption, this t will be finite, which is already kind of necessary. And then because of the second assumption, it will be increasing along future-directed causal curves. Because if I take a future-directed causal curve and I take 2 points, then I look at their pasts, and the past of the point that comes later on the curve is bigger than the past of x, and it's bigger by a set with non-empty interior. So then by this property, it will have a larger measure. And then the last property is important for continuity, because if our measure was something like this, for example, plus a delta, then in the moment where the delta is here and I cross over it, the function would jump. And we don't want to have that, so to exclude that from happening, we impose this third property. Okay. And now on Lorentzian length spaces, what are we going to do? Well, we also choose a measure, but we're not imposing the third property because it's not clear if such measures exist. Because in the manifold case, we know that the boundary of the past is a codimension 1 submanifold, and then it's clear that such measures exist, but here we don't. Right, I'm talking about the smooth case, yeah, sorry, yeah. But then what do we do? So what we do is we choose a thickening of the past. So this I minus sub r of x, the sub r means that I take a thickening of thickness r of the set, and then I integrate over r, and this way, if there's a delta somewhere, then instead of incorporating it suddenly, as I go over it, I incorporate it kind of gradually, and this will ensure continuity. Okay. And that's all I wanted to say about the proof. Later, and by the way, this is why I needed second countability to have existence of a measure with the first two. Yeah.
This is the case. When you cannot leave, you can reverse the contraction and once every time function in the main.
I never thought about it. I don't know. Maybe. But you would have to think how to measure sets that are not the path of a point. Yeah. But maybe it's possible. Yeah.
I don't know.
Maybe
it's more complicated than what I thought. Yeah.
Okay. Right. So now I want to talk about the application that I mentioned of topology change. So basically, in the manifold case, when you have a Cauchy time function, it means that it implies that the manifold will split as a product of R times S, and here S could be like any level set of the Cauchy time function, and they will all be diffeomorphic to each other. And if the Cauchy time function is even smooth, then you also see that the metric splits in this orthogonal way. But notice that here beta is a function of all the variables, so it's not a product manifold. It's not even a work product, no. And this H is a Riemannian metric on S that depends on T smooth. Okay. But then this is not the case for Lorentzian length spaces. So we can have topology change, by which I mean that the level sets of the Cauchy time function can have different topology from each other. And the idea of topology change was considered in the quantum gravity community already before Lorentzian length spaces existed. And in particular, there is a systematic program by Sorkin and others, Dauker, Berle, who wanted to study topology change in a systematic way using Morse functions. And I have an example on the next slide. So we take a cobordism, so a manifold with boundary where we have kind of two pieces of the boundary with different topology now. And then the Morse function here would be just the height function. And then the idea is we want to put a metric on this, which looks roughly like this, which was the thing we had for globally hyperbolic spacetimes. But of course, at the critical points of the Morse function, which is in some sense exactly where the topology changes, this metric will degenerate because there the differential of T is equal to 0. Okay. But nonetheless, one can consider if this still models spacetime in the physical sense. And indeed, I argued in this paper that such an object can still have the structure of a Lorentzian length space in some cases. Actually, not in the case of the picture, but the kind of good cases are all in dimension at least 1 plus 3, so I couldn't put a picture of that. Okay. I'd love to say more about this, but I don't have time, so I'm going to the other topic now. So if you were falling asleep, you can come back now. So I'm going to talk about the completeness of the null distance in the setting of C2 spacetimes. So I'm going to say what the null distance is briefly, although it was already in the talk by Anna. And I mean, the reason it has to do with the other things I was talking about is because it uses a time function in the definition. So the idea is the following. Basically, we take 2 points, x and y, and then we look at piecewise causal curves connecting them. So they are curves where every piece is causal, but it's possible that some are future directed, some are past directed. And then for every of these pieces, I can label them like 1, 2, 3. And for each of these pieces, I look at how much the time function varies on that causal piece. And then this defines the null length with respect to t of this curve. Let's call it beta. So that's the sum of these increments, but in absolute values. If you go up and down, it doesn't cancel, but it comes twice. Yeah. And then the distance between x and y is the infimum of the length over such curves. And this, under some mild assumptions on the time function, this induces a metric space structure. And then the thing that we showed with Aniket is that if there exists a time function such that the null distance is complete, then the manifold is globally hyperbolic at the spacetime, and also the other way around, so if and only. And I can give a short sketch of the proof. So first, the one direction. If the null distance is complete, then you're globally hyperbolic. This is the easier one because, well, suppose the opposite. Okay, so suppose suppose the opposite of this arrow here. So suppose that T is not Cauchy. So if T is not Cauchy, then there must exist at least one inextendable causal curve where the time function does not go to plus infinity, but it stays bounded by some constant. So some constant smaller than infinity. But if this is the case, then if I take points on the curve, so say if it's parametrized on all of R, I just take them like this, then this is a Cauchy sequence. Here, Cauchy is in the sense of metric spaces, has nothing to do with Cauchy here. Yeah? Then this is a Cauchy sequence, and it doesn't have a limit because the curve is inextendable. Inextendable. So now I've shown that if T is not Cauchy, then the metric space cannot be complete. So negating that, I get that if the metric space is complete, then T must be Cauchy. And then by the theorem that I had in the first part of the talk, having a Cauchy time function is the same as being globally hyperbolic. Okay, so we have shown now this implication from left to right. Continuous. T is continuous. I'm not necessarily saying it's smooth. And now to show the other direction. So if M is globally hyperbolic, then there exists a thing called an H-steep temporal function. And let's put it here. I don't know. Here. So that means the following. So it's a time function that is differentiable, so I can consider the differential. And I'm saying that this should be larger or equal than the norm of the vector with respect to H. So there's this H here, and this H is some complete Riemannian metric. I don't care exactly which one. Okay, and I'm demanding this for all V causal vector. So the existence of such a H-steep temporal function was shown independently by Bernatsu and Minguzzi for other reasons. But it turns out that these make the null distance complete. And the idea somehow is that if you're H-steep, then you have a kind of anti-Lipschitz property, because somehow you're saying that the time function grows faster along a causal curve than the length of the curve. And it was already known from before in a paper of Allen and Burch that if you have a time function that has this kind of anti-Lipschitz property with respect to a complete metric, then the null distance is also complete. Okay. And this finishes the proof, basically. And then let me just give the open questions. So first, can we do this on Lorentzian length spaces? Do we have a notion of H-steep time function? So probably defining it is easy because you can just require this anti-Lipschitz directly, but then existence is unclear. And that is obviously related to when is the null distance complete on a Lorentzian length space. So by the way, the null distance on Lorentzian length spaces was already considered by Kunzinger and Steinbauer. where they studied convergence. And okay, so these are two open questions. Another open question is, before I had this construction with the measures, where I had to do this thickening of the boundary of the past to ensure continuity. But after our paper, later there came a paper by McCann and Zeeman where they define a notion of Lorentzian Hausdorff measure. And it's possible that this measure maybe has the right properties to ensure continuity without this averaging procedure, but I don't know. And then also, since I mentioned topology change, it is my understanding that there's still a debate in the physics community about whether topology change is something that we want to consider or not. So I think it's interesting to have more mathematical characterizations of it. And that's it. Thank you for listening.